What lies at the center of the universe? It's a question that has captivated human thought for thousands of years, one that blends curiosity, science, and philosophy into a mystery that challenges the limits of our imagination. When we ask if the universe has a center, we are not just asking about a place on a cosmic map. We are questioning whether reality itself has a focal point, a single origin, or whether it is something entirely beyond our human capacity to comprehend. The mystery is made even more fascinating by the fact that every answer we've given through history has reflected not just our observations, but also the way we see ourselves in relation to the cosmos. Is the universe structured around us, around our galaxy? Or does it expand in such a way that no single center exists at all? Long before the advent of telescopes or modern astronomical tools, humanity's understanding of the cosmos was shaped entirely by what could be observed with the naked eye. Ancient sky watchers across disparate civilizations developed intricate systems for tracking the night sky, noticing the steady and repeating patterns of celestial objects. The stars, arranged in constellations, appeared to maintain fixed positions relative to one another, creating a stable and predictable celestial backdrop. Every night, the stars would seem to rotate around a fixed point in the sky, the celestial pole, leading observers to a sense of cosmic stability. They noticed that certain stars and constellations were seasonal, appearing only during specific times of the year, and they began linking these cycles to agriculture, timekeeping, and navigation. The moon, with its clear and regular phases, offered a precise celestial clock, while the sun's daily journey across the sky provided a rhythm that structured human life and even mythologies. By mapping these motions, early astronomers realized that the cosmos operated under patterns and order, giving rise to the fundamental idea that the universe was a coherent and predictable system. Planets, however, were a far more perplexing aspect of the sky. Unlike the fixed stars, these wandering bodies, Mercury, Venus, Mars, Jupiter, and Saturn, did not maintain consistent motion against the stellar backdrop. Sometimes they would move forward steadily, other times appear to reverse direction, performing what we now call retrograde motion. To the human eye, this erratic behavior seemed deliberate yet intelligible, suggesting some grand mechanism behind their movement. Ancient astronomers meticulously charted these motions over decades, recognizing that these celestial wanderers followed specific paths that could be predicted mathematically, even if their paths appeared more complex than the regular motion of the stars. By analyzing these patterns, early observers sought to find a framework that could explain the order of the heavens, and in doing so, they were led to the idea that there must be a central, unmoving point around which everything else revolved. Cultural interpretations of the cosmos reinforced this notion. In Mesopotamia, Babylonian astronomers created highly sophisticated star catalogues and predictive tables for planetary positions, aiming to anticipate celestial events such as eclipses, which were often seen as omens. In Egypt, the stars were closely tied to the cycles of the Nile, and the alignment of monuments and pyramids with certain stars reflected a belief in cosmic order and harmony. Similarly, in ancient China, astronomers meticulously observed the skies, interpreting celestial patterns as messages from the heavens that guided social decisions. Across these civilizations, there was a common thread. The universe appeared as a structured system, where Earth, stationary and central, seemed naturally to be the focal point around which all celestial bodies moved. This interpretation was not merely scientific, but deeply philosophical, entwining human existence with cosmic significance. To ancient observers, Earth was not just a planet among many. It was the axis of the heavens, the center of creation, a privileged vantage point from which the universe's order could be comprehended. Mathematical modeling also played a critical role in reinforcing this geocentric view. Early Greek philosophers, including Plato and Aristotle, argued for a universe in which spheres nested within spheres, each carrying a planet, moon, sun, or star in precise, concentric paths around Earth. Aristotle, in particular, reasoned that Earth must occupy the central position because it was heavy and naturally moved toward the center, whereas the lighter, ethereal elements of the heavens revolved around it. This conceptual framework was both elegant and persuasive. It provided a clear, logical system for the cosmos that matched what could be observed with the senses. The predictability of celestial motion seemed to confirm the model, as the patterns of the sun, moon, and stars could all be neatly explained by circular orbits centered on a fixed Earth. This perspective was further cemented by the work of astronomers like Hipparchus, who developed precise measurements of stellar positions and planetary movements, refining predictive methods while still assuming Earth's centrality. Even though these ancient astronomers lacked telescopes or knowledge of distant galaxies, their observations were remarkably systematic. They recorded data over generations, developed computational methods to predict planetary positions, and attempted to reconcile anomalies in motion with increasingly complex systems of circles and epicycles. The consistency of their records created the illusion of a universe that truly revolved around a fixed center. From the rising and setting of the sun to the periodic retrograde of Mars, every phenomenon seemed to point toward a universe meticulously designed with Earth at its heart. In this sense, early astronomical observations were not merely about watching the sky. They were about imposing meaning, pattern, and order onto the vast and otherwise incomprehensible expanse of space. The belief that Earth was the immovable hub of everything was as much a reflection of human cognition and the search for order as it was of empirical observation. However, while these early observations were impressively detailed, they were inherently limited by human perception. The vast distances of the stars, the unseen scales of space, and the inability to measure motion beyond the solar system all constrained their understanding. Yet, these early astronomers laid a crucial foundation. By carefully cataloguing the positions and movements of celestial bodies, they created the first framework upon which later astronomers could challenge, refine, and ultimately revolutionize humanity's understanding of the universe. Their assumption that Earth must be fixed at the center was logical, given the tools and knowledge available at the time, reflecting both the ingenuity and the constraints of early human science. They observed patterns, formed models, and interpreted the cosmos as a reflection of human-centered logic, setting the stage for centuries of exploration, debate, and discovery that would eventually dismantle the very notion of a universal center. As the careful observations of early skywatchers evolved into formalized systems, the geocentric model of the universe emerged as the dominant framework for understanding the cosmos. This model, also known as the Earth-centered universe, was most famously codified by the Greco-Roman astronomer Claudius Ptolemy around the 2nd century CE. Ptolemy's work, compiled in the monumental text known as the Almagest, provided a detailed mathematical description of the motions of the planets, sun and moon, all revolving around a stationary Earth at the center of the cosmos. His model was not merely philosophical, it was predictive. Using a combination of circular orbits, known as deferents, and smaller circles upon them, called epicycles, Ptolemy's system could account for the apparent retrograde motion of planets and the variations in their brightness, offering a remarkably accurate means of predicting celestial positions. In Ptolemy's geocentric universe, the heavens were structured as a series of nested, concentric spheres, each carrying a planet or other celestial body. The Earth, solid and immobile, occupied the central point, while the Moon, Sun, planets and stars were affixed to spheres moving in complex but orderly paths around it. This model gave a sense of cosmic harmony, a universe that was intelligible, structured, and centered on humanity. The notion that the heavens operated with perfect circular motion reflected a philosophical ideal as much as an observational reality. Circles were considered the most perfect geometric form, suitable celestial mechanics. For centuries, this combination of observation, mathematics, and philosophical reasoning made Ptolemy's geocentric model the uncontested explanation for the structure of the cosmos. Despite its strengths, the geocentric model was not without complications. Observers noticed subtle irregularities in planetary motion that could not be perfectly explained by simple circular orbits. To account for these anomalies, astronomers added more layers of epicycles, making the system increasingly complex. Yet, rather than undermining the model, these refinements reinforced the perception of a meticulously ordered universe. Ptolemy's system offered the illusion of absolute precision, a universe whose apparent complexity could be fully understood through human reason, anchored firmly to Earth. The geocentric paradigm endured for over a millennium because it aligned with both the sensory experience of a stationary world and the philosophical desire for cosmic symmetry. It is remarkable to consider that this intricate Earth-centered cosmos dominated human thought for centuries, shaping not only scientific inquiry, but also culture, art, and spirituality. From Ptolemy's mathematical tables to the elaborate celestial maps produced in medieval times, the geocentric model framed the universe as a place of intelligible order, where Earth was the fulcrum of all motion. People could look up at the night sky and, through the lens of Ptolemy's calculations, see their place in a harmonious system, reassured that the apparent chaos of wandering planets was, in fact, the outcome of predictable laws. Even as observational techniques slowly improved, the deep-seated belief in Earth's centrality made it difficult for alternative models to gain traction. Yet as precise as the geocentric model appeared, it planted the seeds for a revolutionary shift in thinking. By providing a mathematical framework for predicting planetary positions, it allowed astronomers to measure anomalies, test assumptions, and question foundational premises. The detailed records of planetary motion, the reliance on geometry, and the intellectual rigor of Ptolemy's system inadvertently created the conditions necessary for the heliocentric revolution centuries later. The Earth-centered universe, once the pinnacle of cosmological understanding, would eventually be challenged, not through the failure of observation, but through a conceptual leap that reimagined the very center of our cosmic neighborhood. The geocentric model, despite its elegance and centuries of dominance, eventually faced a paradigm-shifting challenge that would forever alter humanity's understanding of the cosmos: the heliocentric model. This revolution began with Nicholas Copernicus in the early 16th century, whose work De Revolutionibus Orbium Coelestium proposed a radical reimagining of the universe. Instead of Earth at the center, Copernicus placed the Sun as the fixed point around which the planets revolved, including Earth itself. This shift was not merely a small adjustment. It upended the long-held notion that humanity occupied a privileged central position in the universe. By reassigning Earth to the role of just another planet in motion, Copernicus introduced a conceptual framework that redefined both the mechanics of the heavens and the philosophical significance of our world. Copernicus's heliocentric model explained many of the anomalies that had plagued the geocentric system, such as the apparent retrograde motion of planets. In the Ptolemaic model, retrograde motion required increasingly convoluted epicycles to account for the backward loops of Mars and other planets. Copernicus showed that these backward motions could be naturally explained by the relative motion of Earth as it overtook slower-moving outer planets in its orbit. The beauty of this model lay in its simplicity. Rather than adding layers of epicycles, it provided a more intuitive, elegant explanation, grounded in the actual mechanics of planetary motion. Although Copernicus's model still relied on circular orbits rather than elliptical paths, his work laid the foundation for a shift in how humans conceived the cosmos, encouraging observers to think beyond the limits of Earth-centered frameworks. The heliocentric revolution gained further momentum through the observations of Galileo Galilei in the early 17th century. Using the newly invented telescope, Galileo provided empirical evidence that directly challenged the geocentric worldview. He observed moons orbiting Jupiter, proving that not all celestial bodies revolved around Earth. He documented the phases of Venus, which could only be explained if Venus orbited the Sun rather than Earth. Through these observations, Galileo demonstrated that the heavens were not a rigid, Earth-centric system, but a dynamic cosmos with multiple centers of motion, undermining the philosophical and theological assumptions underpinning the geocentric model. His work transformed astronomy from a largely speculative discipline into one based on direct observation and empirical validation, bridging the gap between theory and evidence. The heliocentric shift was not only scientific but also deeply philosophical. By displacing Earth from the center, it challenged the anthropocentric worldview that had dominated thought for millennia. Humanity was no longer the focal point of creation. Instead, Earth was one of several planets in a vast solar system, orbiting a seemingly ordinary star. This realization forced a reckoning with the scale and nature of the universe, expanding human imagination and humility in equal measure. It also set the stage for later developments in physics and cosmology, including the work of Johannes Kepler, who refined planetary motion into elliptical orbits, and Isaac Newton, whose laws of motion and universal gravitation provided the mathematical framework for understanding heliocentric dynamics. Yet, while the Sun-centered solar system shifted our perspective on planetary order, it did not imply that the Sun was the center of the universe itself. Copernicus's model applied primarily to our solar system, and early heliocentric proponents were cautious about making claims beyond it. The notion of a universal center persisted, as many still assumed that even if Earth was displaced locally, the cosmos as a whole must have a central point around which galaxies, stars, and celestial spheres revolved. Nevertheless, the heliocentric revolution cracked open the intellectual door, demonstrating that the universe might be far less human-centered than previously imagined. By placing the Sun, rather than Earth, at the center of our immediate celestial neighborhood, Copernicus and Galileo forced humanity to begin grappling with the possibility that the universe might operate on scales and principles that defy human intuition and preference. In many ways, the heliocentric shift marked a turning point, not only in astronomy, but in human thought. It introduced a method of inquiry grounded in observation, prediction, and mathematical reasoning, challenging dogma and privileging evidence over tradition. By removing Earth from the center, it also removed the implicit assumption that any single vantage point in the cosmos could claim universal significance. This conceptual liberation would ultimately pave the way for modern cosmology, a field that seeks to understand the universe on its own terms, independent of human perspective. Copernicus and Galileo thus did more than reposition planets. They redefined humanity's place in the cosmos, setting the stage for a centuries-long journey toward understanding the true nature of space, time, and the elusive question of whether a center exists at all. The heliocentric revolution fundamentally changed humanity's view of the immediate solar system. But as telescopes grew more powerful and observational techniques advanced, it became clear that our Sun was just one star among countless others, and the universe itself was far larger and more complex than anyone had previously imagined. For centuries, the scale of the cosmos was underestimated. largely constrained by the limits of human perception and the optical instruments available at the time. Early astronomers assumed that the stars visible to the naked eye comprised the entirety of creation, with the Sun as the dominant focal point. But as telescopic technology improved in the 17th and 18th centuries, it revealed that the night sky contained countless stars, clusters, and nebulous formations that hinted at structures far beyond the solar system. Humanity began to grapple with a profound realization. Our solar system was not the entirety of the universe, nor was it even central on any larger scale. This shift in perspective was driven by observations of star clusters and nebulae, which at first were poorly understood. Some of these nebulous objects were initially thought to be clouds of gas or unresolved star formations within our own galaxy. Astronomers like William Herschel meticulously mapped the distribution of stars and nebulae, attempting to infer the structure of what we now recognize as the Milky Way. Herschel imagined a vast disc-shaped system of stars, with our Sun located somewhere within it, though he could not determine its exact position relative to the galactic center. Even though his understanding was limited, his work began to challenge the notion of Earth, or even the Sun, as the central reference point for the universe. The cosmos was proving to be staggeringly vast, and its structure was far more complex than the concentric spheres of Ptolemy or the solar-centric simplicity of Copernicus could accommodate. The concept of a galaxy itself as a universe was a revelation that took centuries to crystallize. Before the 20th century, many astronomers assumed that the Milky Way comprised the entire universe, with its faint, diffuse stars marking the boundaries of creation. Observational data suggested that the stars were not uniformly distributed, but clustered in patterns and formations, indicating a system of immense size. Philosophically, this was a profound adjustment. Humanity had long assumed that the scale of the cosmos was comprehensible, perhaps even accessible, but the realization that the Sun was merely one star among billions fundamentally altered our sense of significance and perspective. No longer was Earth the center, nor even our solar system the primary stage. We were inhabitants of an uncharted, sprawling galaxy embedded in an unfathomably larger cosmos. Technological advancements in telescope design, spectroscopy, and photometry during the 18th and 19th centuries further expanded human understanding of the universe. Astronomers could begin to measure distances to stars, analyze their composition, and detect subtle motions within star clusters. These measurements revealed not only the scale of the Milky Way, but also hinted at the existence of structures even beyond it. While the universe once seemed centered on Earth, and later the Sun, the evidence now pointed to a cosmos in which our planetary system was a small part of an immense galactic system, itself likely just one of countless others. The idea of a center of everything became increasingly abstract and elusive. If Earth was not central to the solar system, and the solar system not central to the galaxy, then the notion of a universal focal point was called into question. This period of discovery also began to highlight the limitations of human intuition. It became clear that perceiving the universe from any single point, Earth, the Sun, or even the Milky Way, was inherently restricted. The universe appeared increasingly vast and uniform, but its true structure could not be fully discerned from a single vantage. As astronomers catalogued more distant celestial objects, including star clusters, nebulae, and globular formations, the cosmos revealed itself as a tapestry of remarkable complexity, composed of systems within systems, each operating on scales beyond human comprehension. Our understanding had expanded from the localized mechanics of planetary orbits to the realization that space itself was unimaginably immense, filled with structures that dwarfed the solar system in every dimension. By moving beyond the solar system in human thought, astronomers not only redefined the scale of the cosmos, but also began to set the stage for the concept of galaxies as independent islands of stars. This transition marked a critical turning point in cosmology. It became increasingly apparent that the universe did not have a single, easily identifiable center, at least not in any practical observational sense. Instead, humanity was embedded within a vast, interconnected cosmic web, one in which our position, though observable locally, was almost certainly unremarkable on the grand scale. The shift from thinking about a solar system-centric universe to a galaxy-centric understanding revealed that the cosmos was not only larger than previously imagined, but also more intricate, challenging humans to expand their comprehension of space, scale, and the very concept of a cosmic center. Even as astronomers began to appreciate the vastness of the solar system and recognize the Sun as merely one star among billions, a persistent misconception continued to shape human understanding of the cosmos. The belief that the Milky Way galaxy itself constituted the entirety of the universe. For centuries, the faint band of light stretching across the night sky, the Milky Way, was considered the full scope of creation. Because the Milky Way appeared as a uniform, shimmering swath of stars, and no other galaxies were yet observable with the telescopes of the time, it seemed natural to assume that this system of stars encompassed everything that existed. Within this framework, the Milky Way's own center was often imagined as the center of the universe, a focal point around which all stars, planets, and cosmic phenomena revolved. In essence, the universe had simply shifted scale from the solar system to the galaxy, with the Sun and Earth still occupying a relatively central and privileged position in this larger structure. This misconception was reinforced by the limitations of observational technology. Early telescopes, though revolutionary, lacked the resolving power to distinguish distant galaxies as separate island universes. Many astronomers could see only faint smudges or nebulae in the night sky, which were presumed to be local clouds of stars within the Milky Way rather than entirely separate galaxies. Without the ability to measure vast intergalactic distances, it was reasonable, given the evidence at hand, to assume that the Milky Way contained all that existed. In this context, the notion of a galactic center became a natural extension of human intuition. Just as the Earth had been assumed to occupy the center of the solar system, the center of the Milky Way was imagined to hold similar significance on a cosmic scale. The structure of the galaxy was mapped in broad strokes, with star clusters, nebulae, and the plane of the Milky Way serving as markers of a central organization. Humanity's perception of the universe remained intrinsically anthropocentric, placing Earth, the Sun, and by extension our solar system, within the heart of a seemingly finite celestial arena. Philosophical and cultural assumptions further entrenched this perspective. Just as ancient and medieval civilizations had interpreted the heavens as a reflection of cosmic order and purpose, many astronomers believed that the Milky Way's central regions were of particular importance. The densest, brightest areas of the galactic plane were often thought to be the seat of cosmic activity, or even the origin point of creation. Cartographers of the heavens produced increasingly detailed star charts that highlighted these central regions, reinforcing the idea that there was a privileged location within the universe. The logic was simple. If Earth was at the center of the solar system, and the Sun occupied a special place within the Milky Way, then it followed naturally, in the minds of many, that the galaxy's center could be considered the universal center. This reasoning, while intuitive, was ultimately a reflection of the human tendency to project significance onto familiar scales, rather than a reflection of actual cosmic structure. It was not until the early 20th century that this misconception began to crumble, thanks to the work of astronomers such as Vesto Melvin Slipher and, most notably, Edwin Hubble. Slipher's spectroscopic studies revealed that many of the nebulae previously thought to be local star clouds were actually receding from us at tremendous velocities, hinting that they were far beyond the Milky Way. Hubble built upon these observations by measuring the distances to these spiral nebulae and conclusively demonstrating that they were separate galaxies, each containing billions of stars and spanning distances incomprehensible in human terms. The realization that the Milky Way was but one galaxy among countless others effectively removed any remaining notion of a galactic center as a universal center. No longer could astronomers point to the densest region of our galaxy and claim it as the heart of everything. The universe itself was vastly larger, with structure and order extending well beyond what had ever been imagined. This shift had profound implications for human understanding and cosmology. The idea that Earth, the Sun, or even the Milky Way occupied a central privileged location in the universe was replaced by a vision of a cosmos in which every point could be considered equivalent. The universe was no longer a series of nested, hierarchical centers. It was a vast expanse of galaxies, each with its own internal structure, distributed across a space too immense to comprehend fully. The Milky Way, once assumed to encompass all of existence, became instead one luminous island in an infinite cosmic ocean. This revelation forced a re-evaluation of the very question of a center. If the universe contains billions of galaxies spread over incomprehensible distances, can there be any single point that serves as the center? Or is the concept itself a human projection onto a reality that defies such simplification? The shattering of the Milky Way-centric view of the universe came through the groundbreaking work of Edwin Hubble in the early 20th century, a revelation that expanded human understanding of the cosmos to truly staggering proportions. Before Hubble, astronomers debated the nature of the spiral nebulae scattered across the sky, uncertain whether they were gas clouds within our own galaxy or distant star systems in their own right. Using the powerful 100-inch Hooker telescope at Mount Wilson Observatory, Hubble meticulously observed these nebulae, measuring the luminosity of Cepheid variable stars within them. These stars served as standard candles, allowing Hubble to calculate the distances to these objects with unprecedented accuracy. His measurements confirmed what had once been contentious. These nebulae were not part of the Milky Way, but entirely separate galaxies, each containing billions of stars, planets, and potentially their own solar systems. Humanity's cosmic perspective expanded overnight. The universe was no longer a single galaxy with Earth and the Sun at its center, but a vast, seemingly infinite expanse of galaxies scattered across unimaginable distances. Hubble's work went even further, revealing not just the existence of other galaxies, but also the dynamic nature of the cosmos. By analyzing the redshift of light from distant galaxies, he discovered that almost all of them were moving away from the Milky Way, and crucially, that the farther a galaxy was, the faster it appeared to be receding. This observation provided the first empirical evidence of an expanding universe and directly contradicted any notion of a central, fixed point around which all cosmic matter revolved. If every galaxy appeared to be moving away from every other galaxy, then no single location could claim centrality. The universe was not a static arena with a well-defined center. It was a dynamic, expanding entity, with every point moving outward in all directions. This fundamentally changed our understanding of cosmology, illustrating that the universe was not a neatly nested hierarchy centered on Earth or even the Milky Way, but an immense, evolving tapestry of galaxies extending far beyond our observational horizon. The implications of Hubble's discoveries were profound. By demonstrating that galaxies are scattered throughout the cosmos, He effectively dismantled centuries of anthropocentric thinking and transformed the human conception of place and significance. The sheer scale of the universe became apparent. The Milky Way, once thought to encompass all that existed, was revealed to be only one among billions of galaxies, itself a tiny, unremarkable part of the larger cosmic structure. Distances between galaxies measured in millions of light years emphasized the incomprehensible vastness of space and the limitations of human intuition. Our solar system, our galaxy, and our local galactic neighborhood were no longer the natural reference points for the universe. They were part of a nearly infinite expanse in which no single position held intrinsic centrality. Hubble's work also laid the foundation for modern cosmology, inspiring scientists to develop new models to describe the structure, history, and fate of the universe. Observations of galaxies' distribution and motion led to the formulation of the Big Bang theory, which posits that the universe began as a hot, dense state and has been expanding ever since. In this context, the idea of a central point loses all traditional meaning. The expansion is uniform across space, and every observer, regardless of location, sees galaxies receding away in all directions. Hubble's discoveries, therefore, not only revealed the existence of other galaxies, but also reshaped our understanding of space and time, demonstrating that the cosmos is vast, dynamic, and remarkably uniform on the largest scales. By confirming that galaxies are dispersed throughout the universe, Hubble eliminated the last vestiges of a human-centered or galaxy-centered cosmology. His work established that no point, including Earth, the Sun, or the center of the Milky Way, holds a privileged position. Instead, the universe is a vast expanding network of galaxies, each with its own internal structure, but collectively forming an almost incomprehensibly large cosmos in which traditional notions of a center are rendered obsolete. This revelation reshaped not only astronomy, but also philosophy and human self-understanding, forcing a recognition of our place in a universe far grander and more complex than any previous generation could have imagined. Hubble's insights opened the door to a modern understanding of cosmology, one in which the universe is no longer centered on humanity, but is an expanding, evolving, and profoundly awe-inspiring expanse of matter and energy. The discoveries of Edwin Hubble fundamentally expanded the human perception of the cosmos, but they also raised an even more profound question. If galaxies are scattered throughout the universe and moving away from each other, is there a central point from which everything originates? This question was addressed through the development of the Big Bang theory, a revolutionary framework that radically altered our understanding of cosmic beginnings. Unlike previous models, which often implied a center around which celestial bodies were arranged, the Big Bang presents a conceptually different picture. The universe did not expand from a single point in pre-existing space, but rather space itself began expanding everywhere at once. In other words, the origin of the universe was not a central location. It was a state of extremely high density and temperature permeating all of space. Every part of the universe today can trace its origins back to this same primordial event, implying that the universe does not have a unique spatial center in the conventional sense. The Big Bang theory emerged from a combination of theoretical insight and observational evidence in the early 20th century. Theoretical physicists, including Albert Einstein, initially formulated general relativity, which provided a mathematical framework for understanding gravity not merely as a force, but as a curvature of space-time itself. Solutions to Einstein's equations indicated that a static universe, as had long been assumed, was unstable. Rather, the universe was either expanding or contracting. Building on this framework, Georges Lemaitre, a Belgian priest and physicist, proposed in the 1920s that the universe might have originated from a primeval atom, a singular state from which expansion began. This concept of a beginning for the universe as a whole was initially controversial, challenging both philosophical and scientific intuitions. Nevertheless, the theoretical models predicted phenomena that could, in principle, be observed, setting the stage for empirical verification. Observational evidence for the Big Bang eventually came in the form of the redshift of galaxies and the discovery of cosmic microwave background radiation, CMB. Hubble's observations of galactic redshifts provided clear evidence that the universe was expanding, as light from distant galaxies is stretched to longer wavelengths by their motion away from us. This expansion suggested that, if we extrapolate backward in time, the universe must have been denser, hotter, and more compact in the past. Later, in 1965, Arno Penzias and Robert Wilson detected the faint microwave radiation permeating the cosmos, a remnant heat from the early universe, which perfectly matched the predictions of the Big Bang model. Together, these findings transformed the Big Bang from a theoretical speculation into the prevailing cosmological framework, fundamentally reshaping our understanding of cosmic origins. The profound implication of the Big Bang model for the question of the universe's center is that there is no such center in a spatial sense. Unlike a traditional explosion, which occurs at a specific point in space and sends matter outward into a surrounding void, the Big Bang was an expansion of space itself. Every point in the universe today was once part of this dense, hot state, and as space expanded, all regions moved away from each other uniformly. This is often illustrated using the analogy of an inflating balloon. Galaxies embedded on the surface of the balloon move away from each other as the balloon expands, and no single point on the surface acts as the center of expansion. The key distinction is that the center of the balloon exists in three-dimensional space outside the balloon, whereas the two-dimensional surface represents the universe itself. Analogously, in our universe, there is no outside or external vantage point from which to identify a central origin. Every observer, regardless of location, sees themselves as surrounded by galaxies receding in all directions, giving the appearance of being at the center of the universe center, while, in fact, no unique center exists. This concept fundamentally challenges human intuition, which has long been conditioned to identify origins and centers. The idea that the universe began everywhere at once, with no spatial focal point, requires a shift from thinking about the universe as a structure within space to understanding space itself as dynamic and expanding. Distances between galaxies increase not because they are moving through space from a central point, but because space itself is stretching, carrying all galaxies along with it. From this perspective, every location in the universe is equivalent. No observer is privileged, and the notion of a center loses its conventional meaning. Even our own position within the Milky Way or the local group of galaxies is arbitrary on cosmic scales, as the expansion occurs uniformly across the observable universe. The Big Bang perspective also introduces the concept of cosmic time as opposed to spatial centrality. While there is no unique spatial center, the universe does have a temporal origin. All matter and energy originated from the same high-density state approximately 13.8 billion years ago. This provides a universal beginning in time, even though there is no corresponding center in space. Every point in the universe can be traced back to that primordial moment, but from a spatial standpoint, all points are equally central in the sense that they share the same origin. This distinction between temporal and spatial centrality is crucial for understanding modern cosmology. The universe has a history and evolution, but it does not have a center in space around which everything else revolves. Furthermore, the Big Bang model has profound implications for the scale and structure of the universe. It implies that the universe is homogeneous and isotropic on large scales, meaning that, statistically, the distribution of matter and energy is uniform, and the laws of physics operate the same everywhere. This uniformity reinforces the idea that there is no preferred location or center, as any observer, anywhere in the cosmos, would perceive the same large-scale expansion. Observations of the cosmic microwave background, along with large-scale surveys of galaxy distributions, confirm this homogeneity, showing that the universe has the same structure in all directions, further undermining the notion of a central point. To help conceptualize the counterintuitive idea presented by the Big Bang, that the universe is expanding everywhere at once, with no central point, cosmologists often use the balloon analogy. This analogy is deceptively simple, yet remarkably effective in illustrating how space itself stretches and carries galaxies along, without implying that there is a single central location from which all matter is radiating. Imagine the surface of a balloon, drawn in 2 dimensions for clarity, dotted with small marks representing galaxies. As the balloon inflates, every mark moves away from every other mark. No matter which galaxy you stand on, it will appear as if all other galaxies are receding from you. Importantly, the surface of the balloon itself has no center. The center of the balloon exists in a 3rd dimension outside the 2-dimensional surface, and this external point is not part of the universe. Similarly, in our 3-dimensional universe, the expansion of space carries galaxies apart uniformly, without any external or internal center. The elegance of the balloon analogy lies in its ability to separate 2 often confused concepts: motion through space versus the expansion of space itself. In a conventional explosion, objects fly outward from a central point through pre-existing space. In contrast, during cosmic expansion, galaxies are not moving through space away from some central location. Instead, the very fabric of space is stretching. This distinction is crucial for understanding why the universe can expand everywhere at once without violating the concept of relativity or suggesting a privileged central location. Every point in space participates in the expansion equally, and distances between galaxies increase uniformly. The balloon analogy emphasizes that while galaxies move apart, none of them occupies a special position at the center of the expansion, just as no point on the balloon's surface corresponds to the balloon's physical center in the 3rd dimension. The analogy also demonstrates why it appears from Earth that galaxies are moving away from us in all directions, an observation that initially suggested a central position. From our vantage point, the recession of galaxies is uniform, creating the illusion of centrality, much as a person standing on one point of an inflating balloon perceives all other points moving outward. This illusion reinforces the intuitive but incorrect notion that humans occupy a central location in the universe. The balloon analogy clarifies that this perception is purely relative. Observers on any other galaxy would see the same pattern, with every other galaxy receding from their position. Expansion, therefore, is not relative to any specific location, but is a global property of space itself, underscoring the homogeneity and isotropy of the universe on large scales. Another important feature highlighted by the balloon analogy is that the universe does not expand into a pre-existing void. The expansion occurs within space itself. Unlike inflating a balloon in air, where the balloon's surface grows into surrounding space, the 3-dimensional universe expands in all directions without needing an outside to contain it. This is a subtle but vital distinction. It means that the universe is self-contained. There is no external vantage point from which one could observe the expansion as happening from a central point. All locations are equivalent, and the geometry of space itself determines the relative motion of galaxies. Distances between galaxies increase as a result of this stretching of space, not because galaxies are moving through an invisible medium. The balloon analogy also helps visualize some of the more advanced implications of cosmic expansion. For instance, in the same way that distant marks on the balloon surface move apart more rapidly than closer marks as the balloon inflates, galaxies farther from any given observer appear to recede faster due to the cumulative effect of space expansion. This observation aligns perfectly with Hubble's law, which demonstrates that the velocity at which a galaxy moves away from us is proportional to its distance. In other words, the farther a galaxy is, the faster it seems to recede, a natural consequence of the uniform stretching of space. This relationship does not imply a central location. It is simply a geometric feature of an expanding space where all points move away from each other. The simplicity of the balloon analogy makes it accessible, but it is also flexible enough to capture more subtle cosmological concepts. For example, it can be extended to visualize different possible curvatures of the universe. A balloon with positive curvature corresponds to a closed universe, while a flat piece of rubber sheet expanding represents a flat universe. In all cases, the principle remains. There is no intrinsic center on the surface itself, and the expansion is uniform from every vantage point. This demonstrates why, in cosmology, the question, "Where is the center of the universe?" is misleading. Expansion is a property of space, not a directional motion from a point. Moreover, the analogy helps reconcile the observational evidence from the cosmic microwave background, CMB. Just as marks on an inflating balloon surface recede uniformly, the CMB appears nearly identical in every direction, with tiny fluctuations corresponding to slight variations in early matter density. This uniformity reflects the homogeneity of the universe on large scales and supports the principle that no observer occupies a privileged location. The balloon analogy thus not only clarifies the mechanics of expansion, but also bridges the conceptual gap between observation and theory, showing how a universe that seems to have galaxies moving away from us in all directions can still be centerless. The balloon analogy provides an intuitive framework for understanding a universe that expands uniformly without a center. But the concept is not merely theoretical. It is strongly supported by observational evidence, particularly the cosmic microwave background radiation, CMB. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is the faint afterglow of the Big Bang, a relic radiation that permeates the entire universe. It represents the residual heat from a time approximately 380,000 years after the Big Bang, when the universe cooled enough for photons to decouple from matter and travel freely through space. What makes the CMB so profound is its remarkable uniformity. The radiation is nearly the same in all directions, with temperature variations on the order of only 1 part in 100,000. This uniformity provides compelling evidence that the universe is homogeneous and isotropic on large scales, meaning that there is no preferred location or direction in space. In other words, it reinforces the idea that the universe has no central point from which everything expands. Rather, every point in space shares the same origin and participates equally in the cosmic expansion. The CMB acts as a snapshot of the universe at a very early stage, revealing the conditions that existed when it was still a hot, dense plasma. The slight temperature fluctuations in the CMB correspond to the primordial density variations that would later grow into galaxies, clusters, and large-scale structures. These minute anisotropies are critical because they show that while the universe is extremely uniform, it is not perfectly so. Yet the deviations are random and evenly distributed, indicating that no particular region occupies a privileged central position. Observers in any location in the universe would detect a CMB with the same statistical properties, providing strong observational support for the cosmological principle. The universe is homogeneous and isotropic on the largest scales. This principle underpins modern cosmology and is incompatible with the idea of a unique spatial center. Moreover, the CMB provides evidence that the universe is expanding uniformly. The photons we detect today have been redshifted by the expansion of space, stretching their wavelengths from the visible or infrared to microwave frequencies. The degree of this redshift is proportional to the distance the radiation has traveled, confirming that space itself has been stretching since the universe's earliest moments. This aligns perfectly with the balloon analogy, in which points galaxies move apart as the surface space inflates, and all observers perceive the same relative expansion. The CMB is essentially the cosmic record of that initial expansion, and its uniformity demonstrates that the expansion has occurred consistently everywhere, without originating from a central point. The observable isotropy of the CMB thus provides direct evidence that the universe is centerless in space, even though every observer sees galaxies receding as if they were at the center. In addition to confirming homogeneity, the CMB also imposes constraints on the overall geometry and topology of the universe, which further affects our understanding of cosmic centrality. Measurements of the CMB's slight anisotropies by missions such as COBE, WMAP, and Planck have allowed scientists to determine that the universe is very nearly flat on large scales. In a flat universe, parallel lines never converge or diverge, and the expansion occurs uniformly in all directions. There is no curvature that would imply a unique spatial center, unlike in a spherical or closed universe where a central point could theoretically exist within a finite volume. Even if the universe was slightly curved, the uniformity of the CMB and the statistical homogeneity of matter distribution would still preclude the existence of a physically meaningful center. These observations collectively reinforce the understanding that any perceived centrality is a local illusion caused by the uniform recession of galaxies in every direction. Furthermore, the CMB provides a temporal context that complements our understanding of spatial centrality. While the universe has a beginning in time, the Big Bang, it does not have a spatial beginning in a localized spot. Every point in space today was once part of the hot, dense state that gave rise to the CMB. When we observe the CMB, we are seeing radiation that originated from all directions equally, effectively looking back in time to when the universe was almost uniform in temperature and density. This omnidirectional glow emphasizes that no matter where an observer is located, the early universe looked essentially the same, reinforcing the concept that the universe lacks a unique spatial center. Every location participates in the expansion and shares the same cosmological history. Beyond uniformity, the CMB also offers insights into the large-scale structure and evolution of the universe. The tiny fluctuations in temperature correspond to quantum perturbations that were stretched during cosmic inflation, a rapid, exponential expansion in the earliest moments after the Big Bang. These fluctuations seeded the formation of galaxies and clusters, demonstrating that the present distribution of matter is a consequence of processes that occurred uniformly throughout space. Once again, this universality indicates that no single point could be designated as the center of the universe. All regions followed the same fundamental physical laws and experienced the same expansion, with differences arising only due to local variations amplified over time. The CMB thus serves as both a historical record and a spatial map, confirming that the universe is homogeneous and centerless. Despite the compelling evidence from the cosmic microwave background and the balloon analogy, human perception naturally struggles with the concept of a centerless universe because observationally, it appears as though everything is moving away from us. When we look at the night sky and measure the redshifts of distant galaxies, every galaxy seems to be receding from our vantage point. To an earthbound observer, it gives the intuitive but misleading impression that the universe is expanding outward from our location as if we occupy a cosmic center. This apparent centrality is a consequence of the uniform nature of cosmic expansion. Because space itself is stretching equally everywhere, every observer, no matter where they are in the universe, will see a similar pattern. From our local frame of reference, galaxies in every direction exhibit recession velocities proportional to their distance, giving the illusion that Earth is at the heart of this grand expansion. The effect of this observational illusion can be further understood through a simple geometric perspective. Imagine being on one galaxy and observing all others moving away. The farther a galaxy is, the faster it appears to recede, a relationship quantified by Hubble's law. For someone on another galaxy, the same law holds. All galaxies appear to move away from them as well. This symmetry is why no point in the universe can claim actual centrality. The perception of a center is therefore entirely relative, rooted in our specific observational standpoint, rather than any intrinsic feature of the cosmos. The expanding universe does not define a unique origin in space. Rather, every point experiences the same expansion dynamics. Our eyes and instruments detect recession velocities from our location, but this is not evidence of a privileged position. It is a universal property of the expanding space. Historically, this misleading appearance contributed to the persistence of anthropocentric and geocentric thinking. Before the development of the Big Bang theory and the detailed study of the CMB, astronomers could only observe galaxies from Earth, leading to a natural assumption that these patterns reflected a cosmic centrality. The apparent motion of galaxies away from Earth reinforced the long-standing human bias to interpret observations in terms of a fixed center. Even after Hubble's work revealed the existence of other galaxies and the uniformity of cosmic expansion, it remained conceptually difficult for many to relinquish the intuitive notion of centrality because everyday experiences rarely involve uniform expansion of space itself. This illusion demonstrates how human perception can be deceived by scale and perspective when interpreting phenomena far beyond ordinary experience. The illusion is compounded by the sheer enormity of cosmic distances. Nearby galaxies in our local group sometimes move toward us due to local gravitational interactions, but beyond these scales, the redshift-dominated expansion dominates, giving a clear signal of recession in all directions. To an observer using conventional telescopes and redshift measurements, the pattern seems to place Earth at the center of motion. The crucial insight, however, is that this pattern is observed identically from any other galaxy in the universe. There is no unique vantage point. Every location perceives itself as central only because the expansion is uniform. In other words, the universe does not have a center, but the uniformity of expansion ensures that observers anywhere will perceive themselves as being in the middle. This misleading appearance also emphasizes the importance of scale in cosmology. On smaller scales, such as within galaxy clusters, local gravitational forces dominate, and galaxies move in complex, non-radial patterns. Only on the vast, intergalactic scales of tens to hundreds of millions of light-years does the uniform recession become apparent. The human tendency to extrapolate from local observations can thus create the false impression of a central location. When astronomers plot the velocities of galaxies against distance, the resulting Hubble diagram shows a linear relationship. Farther galaxies recede faster. This universal trend, observable from Earth, reinforces the illusion that all motion originates from here, when in reality, it is the expansion of space itself that produces these velocities everywhere. Modern cosmology addresses this illusion through careful interpretation and the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. This principle clarifies that no observer, whether in the Milky Way or a galaxy billions of light years away, occupies a privileged position. The apparent centrality seen from Earth is entirely an artifact of perspective. Just as a single ant on an inflating balloon would see all other ants receding uniformly in all directions, we see galaxies receding in all directions, creating the intuitive but incorrect perception that we are at the center. Understanding this distinction is critical for accurately conceptualizing the universe's structure and for moving beyond anthropocentric assumptions about cosmic significance. Thus, the misleading appearance of centrality illustrates a fundamental tension between human intuition and cosmic reality. While observations suggest motion away from us in all directions, this is not evidence of a spatial center. It is a natural outcome of uniform expansion. Recognizing this illusion allows astronomers to interpret redshifts, the cosmic microwave background, and galaxy distributions correctly, and it highlights a central theme of modern cosmology. The universe has no unique center, and all observers are equally situated within the expanding fabric of space. This realization challenges centuries of human-centered thinking and reshapes our understanding of our place in the cosmos, emphasizing that what seems central is often just a perspective-dependent illusion. Building upon the realization that appearances can be misleading, modern cosmology formalizes our understanding of the universe's uniformity through the cosmological principle. This principle is a foundational concept in astronomy and cosmology, asserting that the universe is homogeneous and isotropic on large scales. It looks essentially the same in every direction and from every location. Homogeneity means that, on a grand scale, the distribution of matter and energy is roughly uniform throughout space, while isotropy indicates that there is no preferred direction in the cosmos. Together, these properties imply that there is no special vantage point or central location in the universe. This principle provides a conceptual framework to reconcile the apparent motion of galaxies away from Earth with the profound truth that the universe itself has no center. Just as the balloon analogy illustrated how every observer perceives themselves as central, the cosmological principle formalizes this idea mathematically and observationally. The cosmological principle emerged from both philosophical reasoning and observational evidence. Philosophers and astronomers recognized that assuming a central location for Earth or the Milky Way was arbitrary and anthropocentric. If the laws of physics apply universally, it would be unnatural for one point in space to possess any intrinsic specialness. Observationally, the principle finds strong support in the uniformity of the cosmic microwave background radiation, which shows almost no variation in temperature across the sky, aside from minuscule fluctuations of 1 part in 100,000. Large-scale galaxy surveys also confirm that the distribution of galaxies becomes uniform when averaged over scales of hundreds of millions of light years. These observations collectively reinforce the idea that the universe has no edge or center, and that any observer, regardless of location, would see the same large-scale properties. One of the most compelling implications of the cosmological principle is its support for the Big Bang model. If the universe is homogeneous and isotropic, then the expansion revealed by Hubble's observations cannot have originated from a single spatial point. Rather, it must have occurred everywhere simultaneously. This aligns perfectly with the idea that the universe does not have a center. Space itself is stretching uniformly, carrying galaxies with it, and giving every observer the same relative motion of distant objects. The principle therefore underpins our interpretation of cosmic expansion, providing a theoretical foundation for why galaxies appear to move away from us in all directions, yet no observer truly occupies a central position. It turns what might appear paradoxical, our seeming centrality, into a natural consequence of the universe's uniform structure. The cosmological principle also simplifies the mathematical modeling of the universe. By assuming homogeneity and isotropy, cosmologists can construct models of cosmic evolution without needing to account for privileged positions or directions. This has allowed for precise predictions of phenomena, such as the cosmic microwave background's temperature fluctuations, the large-scale distribution of galaxies, and the behavior of cosmic expansion over time. Without this principle, interpreting redshifts, gravitational effects, and the distribution of matter would be far more complex and ambiguous. The elegance of the cosmological principle lies in its ability to unify observations across vast distances and timescales into a coherent understanding of a centerless universe. Importantly, the cosmological principle clarifies why the universe can be both expanding and centerless simultaneously. While individual galaxies move away from each other, this motion does not imply a central origin point. Instead, the expansion is uniform across space, consistent with the isotropy and homogeneity described by the principle. Every point in the universe experiences the same conditions and observes the same expansion pattern. Thus, even though from Earth it looks like galaxies are receding from a central position, this perception is merely a local vantage point illusion. Observers anywhere else would record the same effect, seeing galaxies move away as if they were at the center, demonstrating that centrality is a matter of perspective rather than physical reality. The principle also has philosophical ramifications. By asserting that no location is privileged, it challenges long-standing anthropocentric and geocentric intuitions that humans occupy a special place in the cosmos. Historically, civilizations placed Earth at the center of the heavens, then the Sun at the center of the solar system, and later the Milky Way at the center of the universe. The cosmological principle represents the ultimate break from this pattern, emphasizing that the universe is vast, impartial, and egalitarian on large scales. Every star, galaxy, and cluster of galaxies is subject to the same cosmic expansion and governed by the same physical laws, and no point can claim special significance in the architecture of space itself. Moreover, the cosmological principle guides the search for deeper cosmological truths. By assuming uniformity and isotropy, scientists can explore the universe's origin, evolution, and eventual fate without invoking special positions or asymmetrical conditions. This has allowed the development of models predicting dark energy's effect on accelerating expansion, the growth of cosmic structures from primordial fluctuations, and the possible geometries of the universe. In all these cases, the absence of a center simplifies the underlying equations and provides a framework for interpreting complex phenomena consistently across vast distances. While the cosmological principle and observational evidence strongly support a universe without a central point, the question persists in the realm of speculation. Could there still exist a center of the universe hidden beyond the limits of what we can observe? This line of inquiry delves into the philosophical and theoretical fringes of cosmology, where certainty becomes elusive. Our observations are inherently constrained by the finite speed of light and the age of the universe, defining what is known as the observable universe, a spherical region extending roughly 46.5 billion light-years in every direction. Beyond this horizon lies an unknown expanse of space that we cannot directly observe, and it is within this uncharted territory that the notion of a hidden center could, in theory, exist. Because we can only measure light and radiation that has reached us, it is impossible to definitively claim that the entire universe, including regions beyond our observational limits, lacks a central point. Some speculative models consider the possibility that the universe might possess a global structure that includes a true center, but that this center is forever beyond our observational reach. In such scenarios, our observable universe would simply represent a local patch in a much larger cosmic volume. While this idea is mathematically conceivable, it is largely unfalsifiable. No experiment or observation could reveal such a center, and thus it remains a philosophical or hypothetical construct rather than an empirically supported reality. Even in these models, the local observations within our cosmic horizon would continue to conform to the cosmological principle. Galaxies would appear to recede uniformly. The cosmic microwave background would remain isotropic, and no detectable preferred position would emerge. Essentially, whether or not a distant, hidden center exists, it would be beyond all practical scientific detection, rendering it largely irrelevant to our understanding of the universe from our vantage point. Some cosmologists have explored even more exotic possibilities, such as universes with non-trivial topologies or global geometries that could, in principle, define a kind of central region. For example, a spherical universe could theoretically have a geometric center if considered in a four-dimensional embedding space, or certain models involving multiverse structures could conceptualize a central origin for our particular bubble universe. In these contexts, a center might exist in a higher dimensional sense or as part of a larger cosmological structure, but again, it would lie entirely beyond our observable horizon. From the perspective of an observer within our own universe, any such center would have no measurable influence on local physics or cosmology, leaving the observable universe effectively centerless. It is also worth considering the interplay between cosmic expansion and the concept of a center. Because space itself stretches, any point in the universe behaves as though it is at the center of expansion relative to its local surroundings. Even if a hypothetical global center existed far beyond the observable horizon, the uniform expansion of space ensures that every observer would still perceive themselves as central within their observable patch. This reinforces the idea that the concept of a center is fundamentally relative. What might theoretically exist on an incomprehensibly larger scale does not change the local experience of isotropy and homogeneity. In practical terms, centrality is irrelevant for observers constrained by the finite speed of light, because the dynamics and appearance of the universe remain the same regardless of any hidden structure beyond observational limits. Philosophically, entertaining the possibility of a hidden center challenges our understanding of cosmology as both a scientific and metaphysical pursuit. It highlights the limitations of empirical knowledge. No matter how advanced our telescopes or models become, certain questions may remain inherently unanswerable. Cosmology operates on the principle that observable evidence should guide theoretical frameworks, and by that standard, the universe behaves as though it has no center. The hypothesis of a hidden center exists as a conceptual exercise, reminding us that the universe might hold truths forever beyond human perception, but without observable consequences, it does not alter the current scientific consensus. Even within speculative contexts, the concept of a hidden center does not undermine the core principles of modern cosmology. The Big Bang still represents a universal temporal origin, the cosmic microwave background remains isotropic, and the large-scale expansion continues uniformly. Whether or not a global center exists beyond our horizon, these phenomena are unaffected. The universe behaves as if it is centerless from every observational standpoint. This reinforces a key lesson in cosmology. Questions of centrality are often as much about perspective as about physical reality. Our inability to detect a center does not preclude its theoretical existence, but it does emphasize that, for all practical and observational purposes, the universe lacks a center in space. In summary, while it is theoretically conceivable that a center could exist somewhere beyond our observable universe, such a center would lie forever outside the reach of empirical investigation. Within our cosmic horizon, every observation conforms to a centerless expansion, every point appears isotropic, and the large-scale structure is homogeneous. The possibility of a hidden center is an interesting philosophical notion, but it has no practical implications for our understanding of the universe or the laws of physics as we observe them. The universe, from our perspective, is vast, expanding, and remarkably uniform, leaving centrality as a concept relegated to speculation rather than observable reality. In this way, the universe continues to challenge human intuition, revealing that the idea of a center may be fundamentally alien to the cosmos itself. While the possibility of a hidden center sparks philosophical intrigue, it is critical to distinguish between the observable universe and the whole universe, as this distinction fundamentally clarifies why any notion of a center is relative. The observable universe refers to the spherical region of space from which light has had time to reach us since the Big Bang, roughly 46.5 billion light-years in radius. Within this observable sphere, every observer sees themselves at the center simply because of the finite speed of light. We can only detect objects whose light has reached us, creating a natural horizon. From our vantage point, it may appear that galaxies are expanding away from a central position, with ourselves at the focal point of recession. But this is a consequence of perspective, rather than evidence of a true central point. Every other observer, located in another galaxy, would perceive a similar observable sphere with themselves at the center, revealing that this apparent centrality is purely local and not a feature of the universe as a whole. The whole universe, by contrast, extends far beyond the observable limits. Its full size may be infinite, or it may be finite but unbounded, in which case it wraps around itself in ways that prevent any single point from being identified as a center. Cosmologists do not yet know the exact scale of the universe beyond what we can observe, and due to the limits imposed by the speed of light and cosmic age, any region beyond our observable horizon is fundamentally inaccessible. Therefore, while we can speak of a center of the observable universe, meaning our local sphere from which light has reached us, this has no bearing on the existence of a global center in the entire universe. The observable universe's center is a matter of perspective. It does not imply that space itself has a unique origin point in three-dimensional coordinates. This distinction also helps explain why our local observations appear consistent with the Big Bang model and the cosmological principle. The isotropy of the cosmic microwave background, the uniformity of large-scale galaxy distribution, and the linear relationship of galaxy redshifts with distance all manifest within the observable universe. These patterns are perfectly compatible with an infinite or unbounded whole universe. The apparent centrality is a consequence of being within a finite observational bubble, not a reflection of any cosmic hierarchy or central position. In other words, the observable universe is like a tiny patch on the surface of a vast, possibly infinite balloon. From any point on that patch, it seems as if the observer is at the center, but the entire balloon has no center on its surface. Understanding this distinction also reshapes our perception of cosmic expansion. In the observable universe, every galaxy appears to recede from us because light from distant galaxies takes billions of years to reach our telescopes, giving us a snapshot of motion over immense distances. However, in the whole universe, galaxies are receding from each other uniformly, and there is no privileged central location where the expansion originated. The concept of a center is therefore inherently relative. It exists only when referencing the limits of what is observable from a particular vantage point. When considering the entire universe, which may extend infinitely or in complex topologies, the notion of a center dissolves entirely, leaving expansion as a global, centerless phenomenon. The distinction between observable and whole universes also underscores the limits of human knowledge. While cosmologists can model and measure the properties of the observable universe with remarkable precision, any claims about what lies beyond remain speculative. This boundary highlights a profound epistemological point. Our understanding of the universe is inevitably constrained by what we can detect. Yet even within this constraint, patterns reveal the underlying homogeneity and isotropy that suggest a universe without a spatial center. In other words, even though our observable bubble seems to have a central point, this does not imply that a central point exists in the full, unobservable universe. Every observer anywhere would encounter the same centered perspective within their own horizon, reinforcing the relativity of centrality. This perspective also has practical implications for interpreting cosmic phenomena. For instance, the accelerating expansion driven by dark energy affects all galaxies equally, regardless of their location, ensuring that the apparent recession pattern is consistent across different observational spheres. Similarly, the formation of large-scale structures, the propagation of light, and the evolution of galaxies all occur without reference to any absolute center. Observers constrained to their local horizon see expansion and motion relative to themselves, but these effects are local manifestations of a global, uniform expansion. By understanding the distinction between the observable and whole universe, scientists can correctly interpret these observations without imposing the misleading notion of a spatial center. Ultimately, recognizing the difference between the observable universe and the whole universe provides clarity in the ongoing quest to understand cosmic centrality. The observable universe may create the illusion of a center due to our limited horizon, but the whole universe, whether finite, infinite, or wrapped in a complex topology, remains centerless from a physical and geometric standpoint. This distinction preserves the integrity of the cosmological principle while reconciling our local observations with the broader reality of the cosmos. It reminds us that what appears central from a human perspective is often just a consequence of observational limitations, and that the true nature of the universe transcends human intuition, existing as a vast, expanding fabric of space in which no point is special. Taking the discussion of cosmic centrality one step further, the multiverse hypothesis introduces an even more profound challenge to the idea of a universe with a center. According to this speculative but increasingly considered framework, our universe may be just one of countless others, each a separate bubble within a vast multiverse. These universes could vary in size, physical laws, and fundamental constants, and they might exist simultaneously in higher dimensional space. If this is the case, the concept of a center loses any practical meaning. Not only does our observable universe lack a central point, but the entire multiverse could be so vast or complex that a single meaningful center cannot be defined. Centrality becomes relative, not just within our universe, but across an infinite or unbounded collection of universes, each expanding or evolving according to its own physical parameters. The multiverse concept arises naturally from several areas of theoretical physics, including cosmic inflation, string theory, and quantum mechanics. In the inflationary model, rapid exponential expansion in the earliest fractions of a second could produce numerous causally disconnected regions, each evolving into a separate universe. These pocket universes could contain different distributions of matter, energy, and physical laws. If we live in just one bubble among potentially infinite others, asking where the center of the universe is becomes a futile question. There might be no global reference frame that encompasses all universes in the multiverse, and therefore no universal central point. From this perspective, The very notion of a center may be a concept that is only meaningful within the confines of a single universe, and even there, it remains relative and observer-dependent. In addition to inflationary theory, string theory offers frameworks in which multiple universes arise naturally due to the complex topology of higher dimensions. Each universe might be connected through extra-dimensional branes, or occupy separate locations in a higher dimensional space inaccessible to us. In these models, the space between universes could have its own structure, but this space is not the same as the observable universe, nor is it constrained by the familiar laws of three-dimensional space. As such, even a hypothetical higher dimensional center would have no influence on local physics within our universe, making the concept of centrality purely abstract and practically irrelevant. The multiverse hypothesis, therefore, amplifies the idea that centrality is not a fundamental property of reality. It is a perspective-dependent illusion restricted to limited observational context. The implications of the multiverse extend even further when considering the idea of expansion. Each universe within the multiverse could expand independently, driven by its own vacuum energy or cosmological constant. There may be no synchronization or relationship among the expansions of different universes, and the geometry of one universe has no bearing on another. In this context, centrality is fragmented and context-dependent. Within any given universe, one might perceive local structures as central relative to their surroundings, but this center does not extend beyond the boundary of that universe. When considering the entire multiverse, no absolute central point exists, and the notion of a universal center becomes entirely meaningless, highlighting the limitations of anthropocentric intuition when applied to cosmic scales. Philosophically, the multiverse hypothesis challenges the very notion of spatial relevance. In a single universe model, questions about centrality at least have potential meaning, however counterintuitive the answers may be. In a multiverse, these questions collapse. Any center we could define is strictly local, limited to our observable or theoretical universe, and it cannot represent the entire ensemble of universes. It emphasizes that human cognitive biases, which favor notions of centrality, hierarchy, and uniqueness, may be ill-suited for understanding reality at these scales. The multiverse, if it exists, is a realm in which familiar concepts such as up, down, near, far, or center lose coherence, replaced by a more abstract, relational understanding of space, time, and structure. The multiverse hypothesis also aligns with the idea that observable phenomena within our universe are inherently local. The cosmic microwave background, large-scale galaxy distribution, and Hubble expansion provide a clear and consistent picture of a centerless universe, but only within our bubble. Observers in a hypothetical neighboring universe would have their own observable horizon, their own CMB, and their own expansion patterns completely independent of ours. There is no overarching frame to compare positions across different universes, reinforcing that centrality is an observer-dependent artifact confined entirely within the local universe. The notion of a center becomes not just elusive, but meaningless on the scale of the multiverse. In summary, the multiverse hypothesis elevates the question of a cosmic center from challenging to essentially moot. If multiple universes exist, each independent and potentially governed by different physical laws, there is no global reference point to designate as central. Centrality is relative not only within our universe, but across the entire multiversal ensemble. Every observer, in every universe, perceives themselves as central only within their local horizon, but no absolute central location exists. This perspective underscores the profound shift in human understanding prompted by modern cosmology. The universe, or multiverse, is not constructed around a central point, and any appearance of centrality is an illusion created by our limited observational vantage. By contemplating the multiverse, we confront the possibility that the very idea of a center is not a property of reality itself, but a reflection of human perspective. As we explore deeper into the dynamics of the universe, the phenomenon of dark energy adds another layer of complexity to the idea of a center. Discovered in the late 1990s through observations of distant type Ia supernovae, dark energy is a mysterious force driving the accelerated expansion of the universe. Unlike ordinary matter or even dark matter, dark energy does not clump. It permeates space uniformly and exerts a repulsive pressure that accelerates the stretching of the cosmic fabric. This acceleration fundamentally alters how we perceive the universe's structure and makes the concept of a fixed center even more elusive. In a universe dominated by dark energy, every point in space moves away from every other point faster over time. And this recession is not uniform in the sense of a simple linear expansion. It accelerates, further reinforcing the idea that no single location can claim centrality. The accelerating expansion caused by dark energy means that distant galaxies will appear to recede at ever-increasing speeds, eventually approaching the speed of light relative to us. In practical terms, this will render some galaxies permanently unobservable, as their light will never reach us, effectively isolating regions of the universe from one another over cosmic timescales. This isolation underscores the relativity of centrality. From Earth, we observe a receding universe, but observers in a distant galaxy see the same expansion pattern centered around themselves. The accelerating rate of expansion ensures that these observations remain consistent across all vantage points, making it impossible to define a fixed center, even in principle. Unlike a static or uniformly expanding universe, where one might imagine tracing back to a hypothetical central point, the acceleration induced by dark energy creates a dynamic, ever-changing framework in which any notion of a central location is transient and ill-defined. Dark energy also interacts with the geometry of space in profound ways. General relativity tells us that the expansion of the universe is influenced by its energy content, including matter, radiation, and dark energy. In a universe with a significant dark energy component, the geometry tends toward a flat or nearly flat configuration on large scales, but with expansion accelerating exponentially over time. This rapid, uniform expansion further reinforces isotropy and homogeneity, meaning that every region experiences the same acceleration regardless of its location. Consequently, the concept of a spatial center becomes meaningless. Space itself stretches between all points, and every observer sees themselves at the heart of local expansion, even though no true central point exists. The acceleration ensures that apparent centrality is always relative, never absolute. The influence of dark energy on cosmic evolution also reshapes our understanding of the observable universe versus the total universe. Because the acceleration increases over time, the observable horizon grows more slowly than in a non-accelerating universe. Regions currently within reach may eventually become causally disconnected, creating isolated pocket regions where galaxies can no longer communicate via light or gravitational influence. From the perspective of an observer in any one pocket, the local universe appears to have a center, their vantage point. But this is purely an observational artifact. On cosmic scales, the acceleration driven by dark energy ensures that all locations are equivalent in terms of the laws of physics and the perception of expansion, eliminating the possibility of a privileged or central position. Additionally, the presence of dark energy challenges classical intuitions about the origin and evolution of the universe. In a decelerating or static universe, one might imagine tracing back the motion of galaxies to a central origin point in space. However, with accelerated expansion, the trajectories of galaxies are not simple linear paths. They are influenced by the stretching of space itself in a way that no single point can serve as the definitive center. Even in principle, there is no fixed location from which the expansion can be said to originate, because the expansion occurs everywhere simultaneously and accelerates over time. This underscores the counterintuitive nature of cosmic expansion. Apparent motion away from an observer does not imply a central origin, especially when that motion accelerates across all points equally. The accelerating expansion also ties back to the balloon analogy, but with an important modification. In a simple balloon analogy, points on the surface move away from each other uniformly as the balloon inflates. With dark energy, imagine the balloon stretching faster and faster over time, causing distant points to recede more quickly than nearby ones. From the perspective of any point on the balloon, it still seems as though that point is central relative to the motion of all other points. However, the acceleration guarantees that this centrality is purely illusory and continually changing in terms of the observable dynamics. There is no fixed anchor point. The universe expands everywhere, faster than the speed of local recession at large distances, ensuring that any hypothetical center is not only unobservable, but fundamentally undefined. In essence, dark energy and the accelerating expansion of the universe reinforce the centerless nature of cosmic structure. The expansion is uniform yet dynamic, isotropic yet accelerating, creating an environment in which every observer perceives themselves at the heart of local motion while no absolute center exists. The acceleration of space stretching magnifies the illusion of centrality within the observable universe, while simultaneously rendering the idea of a true, fixed center across the entire universe practically and theoretically meaningless. Dark energy transforms the universe from a static or slowly expanding system into a dynamic, evolving cosmos in which centrality is entirely relative, further challenging human intuition and reshaping our understanding of our place in the cosmos. Another crucial layer in understanding the concept of a center lies in the theoretical models of the universe's shape, which directly influence whether a central point could exist. Modern cosmology explores three primary possibilities for the large-scale geometry of space: flat, spherical, positively curved, and hyperbolic or toroidal, donut-shaped universes. Each of these geometrical frameworks carries profound implications for centrality and the overall structure of the cosmos, and their consideration helps clarify why the universe may fundamentally lack a center, regardless of appearances. A flat universe is the simplest and currently most widely supported model according to observations of the cosmic microwave background radiation, particularly those from the Planck satellite. In a flat universe, space extends infinitely in all directions, with Euclidean geometry applying on the largest scales. Parallel lines never meet. The angles of a triangle sum to 180 degrees, and there is no curvature that would suggest a central point. In such an infinite or unbounded flat cosmos, the notion of a center is essentially meaningless. All locations are equivalent, and the expansion of space occurs uniformly everywhere. Every observer sees themselves at the center of their observable horizon, but no single point serves as a unique spatial origin. This geometry aligns closely with the cosmological principle, reinforcing the absence of a preferred location in space and the centerless nature of the universe. In contrast, a spherical or positively curved universe can be visualized as a three-dimensional analog of the surface of a sphere in higher dimensions. In this model, space is finite but unbounded, meaning that if you traveled far enough in a straight line, you could eventually return to your starting point, much like circumnavigating the Earth. The concept of a geometric center in a spherical universe is subtle. While the space itself has a center in a higher dimensional embedding, that center does not exist within the three-dimensional universe experienced by observers. From the perspective of beings living in the spherical cosmos, no point is privileged, and the universe still appears homogeneous and isotropic. In other words, even though mathematics allows us to define a center in a higher dimensional sense, this center has no physical relevance for inhabitants of the universe. It cannot be observed, and it exerts no special influence on the expansion of space. More exotic possibilities, such as a toroidal or donut-shaped universe, introduce even more counterintuitive implications for centrality. In these models, space loops back on itself in one or more dimensions, creating a topology in which traveling in a straight line could bring you back to your starting point along a different path. A toroidal universe is finite in volume, yet lacks boundaries or edges, and any attempt to define a central location becomes entirely arbitrary. The geometry ensures that every point is equivalent, and the perception of a center is purely a matter of relative positioning within local observational limits. Like the flat and spherical models, the toroidal universe aligns with the cosmological principle. The universe appears the same in every direction, and no observer occupies a privileged central position. Such topologies illustrate the profound ways in which cosmic geometry can undermine intuitive notions of a center. These models also influence how cosmologists interpret expansion and motion. In a flat universe, expansion carries galaxies apart linearly and uniformly. In a spherical universe, expansion follows curved trajectories in a finite but unbounded space. And in a toroidal universe, expansion can occur along looping dimensions. In all cases, the apparent recession of galaxies from any observer remains consistent, maintaining the illusion that every observer occupies a central vantage point. The shape of the universe, therefore, shapes our understanding of centrality. Even in finite or curved geometries, there is no observable central location within the three-dimensional universe itself. Centrality only exists as a mathematical artifact when considering higher dimensional embeddings or abstract models. Theoretical considerations of shape also tie directly into questions of cosmic topology and connectivity. For instance, a spherical or toroidal universe could produce multiple images of the same galaxy due to the looping nature of space, leading to fascinating observational phenomena without implying a center. In flat and infinite universes, the distribution of galaxies can be statistically uniform over infinite distances, again reinforcing that no location is special. In all these frameworks, local observations, such as redshift surveys, galaxy distributions, and the cosmic microwave background, remain centerless, confirming that apparent centrality is purely a consequence of perspective and observational horizons rather than a property of space itself. Importantly, these theoretical models underscore the interplay between geometry and the physical laws governing expansion. In flat, spherical, or toroidal universes, general relativity dictates how matter, energy, and dark energy influence curvature and expansion dynamics. Regardless of the shape, the uniformity of expansion combined with the isotropic distribution of matter ensures that no observer experiences a unique position or centrality. This further reinforces the conclusion drawn from observations and the cosmological principle. The universe, in all likely geometrical configurations, has no observable center, and the perception of centrality from Earth or any other vantage point is fundamentally illusory. In conclusion, the universe's shape, whether flat, spherical, or donut-shaped, profoundly influences how we conceptualize centrality. Flat universes render the idea of a center meaningless across infinite space. Spherical universes hide any higher dimensional center beyond the observable three-dimensional cosmos, and toroidal universes remove centrality entirely through looping topologies. In all scenarios, the expansion of space, governed by general relativity and accelerated by dark energy, maintains isotropy and homogeneity, ensuring that every observer sees themselves at the center of their observable universe, while the universe as a whole remains centerless. Theoretical models of shape thus provide a geometric and mathematical foundation for understanding why the universe lacks a fixed, observable center, uniting observation, theory, and cosmic geometry into a coherent picture of a centerless cosmos. Even after considering cosmic geometry and expansion, one of the most striking aspects of the universe is how profoundly perspective shapes our perception of centrality. The idea that we are at the center of the universe is, in many ways, an illusion created by the uniform expansion of space and the finite speed of light. From any vantage point within the universe, it appears as though all galaxies are moving away from the observer, with more distant galaxies receding faster than closer ones. This phenomenon arises naturally from the metric expansion of space. As space itself stretches, distances between galaxies increase, and this increase is proportional to distance, as described by Hubble's law. The result is a visual impression that we occupy a central position, when in fact, this effect is identical for every observer located anywhere in the universe. The illusion of perspective can be better understood through the lens of the cosmic horizon. Each observer, constrained by the distance light has traveled since the Big Bang, has a finite observable universe surrounding them. Within this spherical horizon, all galaxies appear to recede from the observer, creating the impression of centrality. Yet, an observer in a galaxy billions of light years away would see the same phenomenon. Their local horizon would encompass galaxies, moving away from them in every direction, just as ours does. The centrality is therefore relative, not absolute. It exists only within the confines of the observer's horizon. The universe lacks a privileged point, yet every location is locally central from its own observational frame. This relativity of perspective reveals the deeply counterintuitive nature of cosmic structure. Appearances from a single vantage point can be profoundly misleading. The balloon analogy illustrates this principle with remarkable clarity. Imagine dots drawn on the surface of a balloon as it inflates. Each dot observes all other dots moving away from itself, with more distant dots receding faster. No dot occupies a true central position on the balloon's surface, yet each experiences the same illusion of being at the center. Replace the balloon's two-dimensional surface with our three-dimensional universe, and the effect is the same. Expansion makes every point appear central relative to the observer's location. This analogy reinforces that centrality is not a property of space itself, but an artifact of perspective, arising from the uniform stretching of space over time. Further complicating matters is the accelerating expansion driven by dark energy. As the rate of expansion increases, galaxies beyond a certain distance will eventually move away faster than light can traverse the intervening space. These regions will become permanently unobservable, and the apparent center for any given observer will remain fixed within a shrinking fraction of the whole universe. The illusion of centrality persists and is amplified locally, even as the observable universe becomes an ever smaller patch of the total cosmos. In this way, perspective is not just misleading, it dynamically shapes our observational reality, giving every observer a unique yet equally central viewpoint. This illusion also explains why historical civilizations and even early astronomers consistently place themselves or their environment at the center of cosmic models. When only local observations were available, It seemed as though celestial motions radiated outward from Earth or the Milky Way, reinforcing anthropocentric intuitions. Modern science has shown that these perceptions were artifacts of local perspective and observational limits. No matter how advanced our telescopes or data, the same principle holds. Every observer sees themselves at the center of their observable universe, but no single observer occupies a true central position in the full three-dimensional cosmos. The illusion of perspective extends to the interpretation of cosmological data, including redshifts, cosmic microwave background radiation, and galaxy distributions. Observers interpret receding motion relative to themselves, measure temperature fluctuations relative to their location, and map large-scale structures from within their horizon. These measurements are internally consistent and obey physical laws, yet they create a subjective experience of centrality that is entirely local. The uniformity of these observations across all directions ensures that the universe's expansion appears isotropic from every vantage point, reinforcing the notion that centrality is illusory and perspective-dependent. Philosophically, the illusion of perspective challenges the human tendency to perceive a privileged position in the cosmos. It forces us to confront the idea that our intuitions, shaped by local and everyday experiences, are ill-equipped to grasp the true scale and structure of the universe. While it may feel natural to imagine ourselves at the center, modern cosmology demonstrates that this is a perceptual artifact. Expansion, isotropy, and the finite speed of light conspire to place every observer at the apparent heart of their observable universe. In reality, no special position exists. The universe is uniform and centerless, and centrality is a product of observation rather than an intrinsic feature of space. After considering the illusion of perspective, the accelerating expansion driven by dark energy, and the implications of cosmic geometry, we arrive at what is arguably the most robust conclusion in modern cosmology. The current scientific consensus firmly asserts that the universe has no center. Observations across multiple lines of evidence, from galaxy redshift surveys to the cosmic microwave background, from large-scale structure mapping to Type Ia supernova measurements, consistently demonstrate that the universe is homogeneous and isotropic on the largest scales. This means that, statistically, every region of space is essentially equivalent to every other, and no single location is privileged as the central point of expansion. The expansion of space occurs everywhere simultaneously, and from every vantage point, it appears that galaxies are moving away from the observer in all directions, giving the illusion of centrality without implying a true center. Hubble's law remains a cornerstone in establishing this centerless model. By observing that galaxies are receding from us at speeds proportional to their distance, Edwin Hubble provided the first empirical evidence that the universe is not static and that expansion is uniform on cosmic scales. Importantly, this expansion does not imply that Earth, or any other location, occupies a central position. Rather, every point in space experiences the same relative expansion, and every observer would measure the same linear relationship between distance and recession velocity. This universal applicability confirms that centrality is an observational artifact, a consequence of perspective rather than a physical reality. Further support for a centerless universe comes from the cosmic microwave background, CMB. The CMB, a relic radiation from approximately 380,000 years after the Big Bang, is remarkably uniform in all directions, with only tiny fluctuations that correspond to the seeds of galaxy formation. The isotropy of the CMB indicates that the early universe was nearly uniform and that no point in space was privileged over any other. If a true center existed, we would expect to see anisotropies or directional biases in the CMB corresponding to the distance from that center, but no such evidence has been observed. This reinforces the prevailing view that expansion is a universal phenomenon occurring everywhere equally without a spatial center. Dark energy and the accelerating expansion add another layer of confirmation. Because this mysterious force acts uniformly throughout space, every point experiences the same accelerated stretching. Observers everywhere see galaxies moving away in a manner consistent with Hubble's law, and the apparent centrality at any given vantage point is again purely relative. The presence of dark energy does not create a center. Instead, it ensures that expansion continues uniformly and isotropically, reinforcing the scientific consensus that the universe has no central location. Theoretical considerations from general relativity also support this view. Einstein's equations allow for a universe that is homogeneous, isotropic, and either infinite or finite, but unbounded. In both scenarios, there is no preferred location in space, and the expansion occurs evenly in all directions. Whether the universe is flat, spherical, or toroidal, the governing laws of physics do not distinguish any one point as a center. This convergence of observation, theory, and geometry has led cosmologists to a remarkably consistent conclusion. Centrality does not exist in the physical structure of the universe. The implications of this consensus extend to both practical observation and philosophical reflection. Practically, it means that no matter where humanity might travel, whether to a distant star system, another galaxy, or even a far-flung region near the edge of the observable universe, every observer will perceive themselves at the center of their own observable horizon. Philosophically, it challenges anthropocentric intuitions that place humans or Earth at the focal point of cosmic significance. Modern cosmology instead presents a universe in which space itself is the stage, expanding uniformly and inexorably, with no spatial hierarchy or privileged position. In summary, the current scientific consensus is unequivocal. The universe has no center. Expansion occurs everywhere equally, and every observer perceives themselves at the heart of their observable universe. But this centrality is entirely relative. Observational evidence from galaxy motion, the cosmic microwave background, and large-scale structure, combined with theoretical models from general relativity and cosmological geometry, all converge on the same picture: a centerless cosmos, expanding uniformly in all directions. The universe is not built around a focal point. It is an ever-expanding, homogeneous, and isotropic fabric of space, where centrality is a matter of perspective rather than a fundamental feature of reality. This understanding challenges our intuition, redefines our cosmic position, and underscores the profound elegance and scale of the universe we inhabit. As we draw this exploration to a close, it becomes clear that the question, what is at the center of the universe, may itself be a relic of human intuition rather than a meaningful cosmic inquiry. For centuries, humans have sought a focal point, a place of origin, a center around which all things revolve, perhaps because our everyday experience is grounded in finite, bounded environments where centrality is obvious and intuitive. From the Ptolemaic geocentric model to the first inklings of the heliocentric solar system, we have repeatedly projected this desire onto the cosmos. Yet, as modern science reveals, the universe operates on principles that defy these intuitions. Expansion occurs everywhere. Isotropy and homogeneity dominate, and the very geometry of space can render the concept of a center meaningless. The mystery lies not in locating a center, but in comprehending a reality where centrality does not exist. This realization carries profound philosophical and scientific implications. It forces us to confront the vastness and impartiality of the cosmos, No point is privileged, no observer occupies a special position, and the universe expands uniformly, without hierarchy or preferred direction. The apparent centrality we experience, every observer sees themselves at the heart of their observable horizon, is an artifact of perspective, a trick played by the finite speed of light and the limited reach of our observation. Even with the most advanced telescopes and the most refined measurements, the fundamental centerlessness of the cosmos persists, suggesting that the universe is far stranger and more elegant than any model built around a central point could convey. In a way, the absence of a center liberates our understanding. It challenges anthropocentric thinking, reminding us that humanity is not at the focal point of creation, but part of a vast, interwoven fabric of space and time. It allows us to appreciate the universe as a dynamic, ever-expanding system, governed by laws that apply equally everywhere, transcending the need for a spatial anchor. The universe is not designed around human perception, and its structure is indifferent to our desire for a central place. This awareness fosters humility, but also awe. The cosmos is not just vast, it is fundamentally egalitarian in its spatial structure, where every location is as central or as non-central as any other. Moreover, the unanswered questions that remain add to the wonder. Could there be regions beyond our observable universe that follow different expansion histories? Might dark energy, dark matter, or the topology of space hold deeper surprises we have yet to grasp? Could multiverse frameworks, higher dimensions, or unknown physical principles further transform our understanding of cosmic structure? These possibilities suggest that the universe's centerlessness is not a limitation, but a doorway into deeper inquiry. The mystery is no longer a puzzle to pinpoint a center, but a profound reflection on the nature of space, time, and observation itself. Ultimately, the greatest lesson from this exploration is that the universe defies simplistic human expectations. Asking for its center assumes a structure it does not possess, yet this very assumption drives curiosity, exploration, and discovery. In the absence of a center, we find a universe more intricate and expansive than our ancestors could imagine. A universe where expansion, geometry, and perspective converge to create an elegant, centerless tapestry. It is a cosmos that humbles and inspires, reminding us that the mysteries of space are not always answered by pointing to a location, but by understanding the principles that govern the entirety of existence. So, when we ponder what is at the center of the universe, perhaps the most remarkable answer is that there may be no center at all. The true mystery lies in comprehending a universe that is infinite, or at least unbounded, where expansion occurs everywhere equally. Perspective shapes perception, and every observer experiences their own local center without implying a global one. This realization transforms the question itself, turning it from a search for a point into an appreciation of the boundless, centerless expanse we inhabit. It is a reminder that the universe is not built around us or any point, but exists as a dynamic, evolving, and incomprehensibly vast reality, whose centerless nature challenges, inspires, and continually expands the horizons of human understanding. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.